All right, recording's rolling. So today is Monday, November 29. Welcome back from a long Thanksgiving break. All right, so you guys know we have 3 weeks and 2 days until next break. And well, here's a bunch of stuff I hope you get in for then. We got to finish rotational dynamics. Now, you guys remember before the break, I gave you guys all the notes on this. So you guys do have the notes already. And then Um, oh yeah, you guys did O'Neill Cylinder a couple days before, and so got that got them hung up by class. Check it out. Right. Oh, so got to go over the homework puzzles, which look like these. Now this page I gave you guys a long time back, so a few weeks back. So I probably have this. Right. Remember, if you lost any of these pages, they're also on Google Classroom. Right. So we'll do as many of these as we can today. Now I do have a bunch of labs I'd like to get in before we start the midterm review too. Midterm review, by the way, I do have for you guys also. This is clipped to the side of your desk. You guys see on the right side, a half page looks like this. So as soon as we finish rotational dynamics here in a couple of weeks, then we will start that midterm review. Right, but you guys have it in your hands right now. Also, you may have noticed that on Google Classroom, I did post a few other pages that will be helpful for the review that you guys do have already. You guys remember the very first day of school you walk in, there's this variables table, there's this grade page looks like this. And there's also AP's equations. So I went ahead and posted that too because it's really similar content. Okay. All right, so you guys got all those materials. All right, so let's jump into these problems then. Like I said, we'll do as many as we can today, and then some of these labs we'll save for later this week. Okay, number 67, the first one. Yeah, got flat tire. Suppose your car has a flat tire. You get out your tools and find a lug wrench to remove the nuts off the bolt studs. You find it impossible to turn the nuts. Your friend suggests ways that ways you might produce enough torque to turn them. What are 3 ways your friend suggests? 3 ways. Okay. So let's get a picture going. So we can figure out from that. Number 67. So you got this wrench, got this lug nut, and this is on here real tight, and we're trying to force it off, and it's just not turning. Okay. Suppose maybe I'm applying a force that's like this, applying a force right there. Okay. And you see me doing that, so I'm grabbing the middle of this wrench, and I'm pushing like that angle right there, sort of like that. Okay. You say, hey, I can help you out because I know some physics. Okay. And I know that maybe this is a question of torque. You guys remember torque? Is R cross F. It's like opening a door. Some radial distance that the door knob might be from the hinges, and you apply a force and it opens the door. Okay. You say, I can give you 3 suggestions that's going to help you out. It might actually loosen that lug nut. What's one suggestion? Maybe one that's like so obvious that I shouldn't even mention it, which is just to apply a maximum force. Okay? So you can maximize the force. Okay? What's another thing you could do? How about what about the location of that force? Is there a better location to press? Yeah, because look at the radial distance that it's taking advantage right here. It's only about half the length of the wrench. See, if you press at the end of the wrench, wouldn't you get twice the torque? If you double that, you double that. Okay. So maximize the lever arm, R. Okay. And there's one more thing you could do, which is what? How about this? see the angle that that force is applied? See the angle? Okay. Isn't it partly pushing towards the lug nut and partially pushing perpendicular to the lever arm? Right? But only the perpendicular part actually does any torque. Right? That's what a cross product is. Right? That multiplication there, that's a special kind of multiplication. It's called cross product. Remember, it has to do with the sine of that angle, right? Just the perpendicular component. So let theta go to 90 degrees. Yeah, those are the three things you could do. Good things. Right, next one, number 74. We got a steering wheel. It's turned through 128 degrees, and the radius of this wheel is 22 centimeters. How far would a point on the steering wheel's edge move? Say you put a little piece of tape right there and then just turn it. Right? How far, say in centimeters, would that move? Right? You know what that is? This is number 74. There is a way you can translate from rotational motion back to linear motion, right? And it's on a poster on the wall. I still haven't printed out the small versions of those for the camera, but do you guys see this poster over here on the wall? This is one, right? Oh, look at that. X equals theta r. Actually, there's a version of this that you've known for probably many years, which is if you make one full trip all the way around the circle, that's called circumference, right? Okay. What is circumference in terms of radius? Circumference equals what? 2 pi r. You guys remember that? Circumference equals 2 pi r. Right? Hey, this is actually a more general version of that. Circumference equals 2 pi r is a specific version of x equals theta r. I'll write that down here. So you've got some angle theta, some radial size r, and some distance x from here, trekking all the way around to here. And that x is equal to theta times r. Now, you might remember from a couple weeks back that there's a catch with this theta, though. And that's that you have to, if you want to play it directly in a formula like this, I don't see any sines or cosines that angle's in. I'm directly multiplying the angle by something. You have to use what measure for theta? You can't use degrees. You have to use what? Radians. Yeah. And the third way would have been revolutions. But yeah, you're right. Yeah. So you're going to use radians. Now, the problem is the book gave it to you in degrees. They said theta is so many degrees. I'll change the number. I'll make it, let's say 99 degrees. I don't know. It's a little bit different from the book. Right? And let's take the R value and make it, 25 centimeters, something like that. Okay. Okay, so we got to do conversion before you can actually start plugging and chugging. Otherwise, we'll get numbers that make no sense. Okay. So how do you convert from degrees to radians? How do you do that? So we got to get rid of degrees and bring in radians. Okay. Well, let's think of some values that might be equivalent, right? Like one full trip around the circle, that would be one revolution. That's, how many degrees is that? One full trip all the way around? It's like 360 degrees, right? And that's also equal to how many radians again? 2 pi. It has to be. Actually, I mentioned a specific example just a minute ago that was that, right? Remember circumference all the way around is equal to 2 pi r? Or something like that? Yeah. So I know that 2 pi radians is equal to 360 degrees. Right? Did you guys see this in a math class at some point? Maybe pre-calc or trigonometry? Right? Or sometimes in a pre-calc or trig book, what they'll say instead is to multiply by pi and divide by 180. Because you see that 2 pi over 360, same thing as pi over 180. But degrees cancel, we're going to end up with radians. So what is 99 times 2 pi on 360? Right, I'm looking at, this is 1.728 radians. Okay. Now, really, that's too many digits, but I'm going to save my rounding for the very end. Okay. Also, I've got this radial size, so many centimeters. No, I changed the numbers from the book, so a little bit different numbers. But, oh, hey, now we can bring in this guy right here. Okay. So how far does something move? X is equal to theta times r. The theta's in radians, 1.728 radians times so many centimeters. Let's see. I'm looking at this many centimeters. All right, there you go. Guess how far that point would have moved. There you go. Right, number 75, propeller. A propeller spins at 1,880 revolutions per minute. Hey, you guys ever heard RPM? RPM? That's what it stands for, right? RPM, revolutions per minute. Okay. But the way your book typed it is actually a better way to think of it because it's like a fraction form, right? Okay, what is the angular velocity in radians per second? Okay. Now, they did give you an angular velocity, they just gave it to you in a unit that you can't directly plug into an equation. But we can do the conversion, so get part A. Okay. And the follow-up question in part B is going to say, what's the angular displacement in so many seconds? You know what? That's actually really similar to what we just did. Not exactly, but pretty close. Right. Let's try this out. 75. Right. Hey, angular velocity. Do you guys remember what the symbol for that is? It's a Greek letter. Omega. You guys know that? Now, for the notes, I'll change the numbers a little bit. Let's say it's an even 2,000 revolutions per minute. And let's say the time interval that it's spinning for is an even 3 seconds. Something like that. Okay. Not exactly what the book says, but pretty close. Okay. So part A, what is the angular velocity in radians per second, which is a more useful number for equations? Well, let's do a dimensional analysis, just like we already did before. Got 2,000 revolutions per minute. Okay. Oh, actually, we need to convert two things to get to radians per second, right? We need to do revolutions to radians, but also minutes to seconds. So it's going to be two conversions. Okay, is it? So set my railroad tracks. Okay. So revolutions to radians. Well, talked about that one already. So one revolution is 2 pi radians. Same thing. Okay. And then minutes. If I put minutes up here, and then 60 seconds down here, you see minutes is going to cancel, and revolutions cancels. And the unit I'm left with is radians per second, which is exactly what we want, radians per second. So multiply across the top, 2,000 times 2 pi, and then divide bottom by 60. I'm looking at this many radians per second. I've got too many digits. I should probably just do 3 significant figures. Okay. Like I don't really know that 0.4 is actually, all I know is like 209. But say if I had like 3 sig figs. Okay. What's part B? Part B says how far does it turn in that time interval? Okay. You guys remember how distance equals speed times time? Okay. Now, what I just wrote is linear. What's that number by? Okay. All right. Now that's for linear motion, but the rotational equivalent is this: how far something turns is equal to how fast it's spinning for how much time. Okay. And we know how fast it's spinning because that was the answer to part A. That's 209 radians per second. And we know the time interval because that was given. So many seconds. You guys see the seconds is going to cancel? And what is that number? Times the time interval? I'm looking at this many radians. If I had 3 significant figures to work with, then I could say how many radians. Right? You know what? I got a couple of follow-up questions of my own about this one, because that's the answer. That's all fine and good. But I wonder how many full revolutions is that? Can anybody figure out how many revolutions that's equivalent to? Like how many full circles does that make? How would you figure that out?
You just divide by 2 pi, right?
Exactly, divide by 2 pi. Yeah. Because 2 pi radians per revolution, right? So take 628, divide by 2 pi. Okay. Can I type it like this? Can I say divide by 2 pi like that?
No.
You're right, I can't, because what's wrong with that?
And divided by 2 and multiply.
Yeah, I see a lot of you guys are seeing that. Right? So if I type it like that, then the calculator divides by 2 and then stops dividing and turns around and multiplies by pi, which gives me an answer that's just not right. Right? So yeah, you guys are right. I do need to group this together in parentheses. Right, now it's divided by 2 pi. So, okay. Now I picked some random numbers, but interestingly, it came up to 99.9. Right? This is, now that's how many full spins it makes. It's like basically 100 full turns with this scenario. Okay? I could ask another question. How many degrees does it turn through? Now, if I start from the revolutions, I could just multiply that by 360 degrees per revolution. It'd be like that many degrees. See if I cared about that. It's a big number. Okay. All right, number 76. Next one. The propeller in the previous problem slows from so many revolutions per minute to so many revolutions per minute, all in some time interval. What is the angular acceleration? 76. All right, they gave us omega naught of so many revolutions. No, I'll make up my own numbers again like I usually do. I'll round that up, I guess, to an even 500 revolutions per minute. And it slows down to omega final of, say, an even 200 revolutions per minute. And it does this all in a time interval of so many seconds. Maybe I'll call it like an even 3 seconds. Okay. So the question is, what's the angular acceleration? That's to say, like, what's the rate that it's slowing down? Oh, I need to give you guys a visual on this. Do that real fast, because I do have this turntable here. Okay. So again, this thing is spin. Okay. Okay. No, if it's spinning at a constant rate, like right now, it has some omega value, right? So many radians per second. If I let it just go though, there's a little bit of friction. It's going to slow to a stop. Like, what rate is it slowing down? That's sort of what we're trying to solve right now. Okay. But we do have to convert these to radians per second. Now, we did that last question. So let's do that real fast. Whip this up, some dimensional analysis type tables. I know there's 1 revolution, 2 pi radians. And 1 minute is 60 seconds. All right. I'm looking at 52.4 radians per second initially.
Mr. Griffin,
Oh yeah,
can you zoom in on it?
yeah. Okay. And then ends up at 20.9 radians per second. Okay. All right. Now, you guys remember kinematic motion? Okay, there's even a poster over here. You guys see this yellow poster on the wall? It has these kinematic formulas that are analogous to these linear motion formulas on this green paper, right? So if you're looking for alpha, like the rate it's slowing down, and you know some omega values in the time, you guys see it's going to be that little one right there? Maybe that one. Okay. So if you go like this, final angular velocity is equal to initial angular velocity plus angular acceleration times time. Okay. Or if you like, no, of course you could plug in this number, and this number right now and just solve it off that way. Okay. If you like it this way though, you could say the rate that it's slowing down is final minus initial angular velocity all divided by the time interval, okay, in terms of variables. Okay. Okay, so it got down to 20.9 radians per second from 52.4 radians per second, and it did this all in like this many seconds. Let's see. All right, I'm looking at this many radians per second squared, because that's the unit for alpha. Okay? Radians per second squared is all alpha. The rate that's slowing down. Yes, sir? Oh. I want to know some other things about this book. So we're done with the textbook question. But can you guys draw a graph about this? So this is still 76. Like if I gave you guys an omega versus time graph, this is of course radians per second, and this would be seconds. Can you guys graph what we just did? So we started here at 52.4 radians per second. It slowed down to 20.9 radians per second. And it did that all in, what did it say, 3 seconds? Like that. So it was initially going this fast. After 3 seconds, it's only going this fast. Now, as long as you assume uniform angular acceleration, would be that, right? And actually, look at what we just found. Change in omega divided by the time interval. Isn't that like rise over run of this line? Doesn't this line right here also represent alpha? Right, the rate that's slowing down. Oh, and also it's negative. Look at that, because it's a negative slope. Okay. You know what else they really could have asked? This would have been the last kinematic value too, is how far did it rotate? Like how many, say, radians did it turn? Or how many revolutions if you wanted to convert after that? Okay. And what property of this graph would tell you that? Of course, you do the equations also, but graphically, it would be what property? You like the area of that trapezoid, right? Radians per second times seconds gives you some number of radians, right? Or, here, so this is theta. You could have said theta is equal to omega naught t plus 1/2 alpha t squared. Okay. We have all these values. This was given, this was given, this we just calculated, and it's negative. Okay. That would also tell you what that is. Number 84. A bicycle wheel with a radius of so many centimeters is given an angular acceleration of this many radians per second squared. By applying a force on the this many newtons at the edge of the wheel, what is the wheel's moment of inertia? Moment of inertia. You guys remember moment of inertia? This is one of these new concepts going back a couple of weeks. Okay. You guys remember these sticks that had these weights at different locations? Okay. So now this one has them really close in, so if I want to shake this back and forth, it's really easy to do. But the other one has these weights pushed really far out. So its mass is the same, its weight is the same, but if I try to shake it back and forth, the other one's really hard to do, and this one's really easy. Okay. Because inertia, up until about a couple of weeks ago, it's just been represented by the mass, but now it's the location of that mass also, and that's what we're trying to find, is what's the moment of inertia. Okay. But we're not going to solve it using mr squared or summing up mr squared. We're going to go about this with the equations through torque is what this is going to be. Okay, so 84, draw a picture for you guys and remind you guys how we were solving this in the notes a while back. So zoom out. Okay, so we got this bicycle wheel. Just like usual, I'm going to make up my own numbers. So say my own radius value. Say radius is equal to, you know what? I'm going to use like a standard type tire. Now, standard tire has a diameter of 26 inches. So divide by 2, that'd be 13-inch radius. Does anybody know exactly how many centimeters there are in 1 inch?
Like 2.5.
It is 2.54. Yeah, that's a definition. So actually, like inches are like tied to the metric system through exactly that conversion right there, like 2.54 exactly. Okay. So I'm gonna have a radius of, let's say 33 centimeters, 33.0 even. So 33.0 centimeters. Okay. standard block tire. And what else did they tell you? They told you angular acceleration. So that's alpha. Number, I'm gonna go say 2.50 radians per second squared. Right? So that's the rate this is speeding up spinning. Because there's a force applied at the edge of the wheel. So you have force of maybe I'll do like 1.5 newtons, something like that. So just making up some numbers. Here we go. Okay. Now let's say that these are at right angles to each other, like that. This is speeding up spinning. Okay. What is the rotational inertia? Okay. Now this is going to go through torque. And so what is I is the question. Okay. So torque. Now I gave you guys two perspectives on torque, and we're just going to relate those to each other and solve it that way. Okay. Now the first way I told you guys about torque, remember I said was R cross F. That's like the wrench problem you guys saw at the beginning of class today. That was like opening a door. You apply a force on the handle that's opposite of the hinges, so you can get a nice lever arm. Right? All it do. Okay. But also torque has another formula, and this other formula is analogous to Newton's second law of motion, but it's in a rotational context. Does anybody remember, or maybe have their notes open and remember what the other formula for torque is? So remember, it's I times alpha. Right? Now this is analogous to F equals ma, except it's rotation. Because well, instead of something accelerating meters per second squared, now it's speeding up spinning, like radians per second squared. That's alpha. Okay. The inertia that would impede that change of motion is not just mass, but now it's how that mass is distributed. So that's I. That's rotational inertia. Okay. And it's not a force that gets that going, but it's a torque. Okay. What we're going to do is we're going to take these two expressions for torque, two different ways of looking at torque. We're just going to set those equal to each other. Say like this expression for torque is equal to this expression for torque. Okay. Why? Because we have three of these four variables. There's R, there's force, and there's alpha. You solve for I. So I times alpha comes from R cross F. Trying to solve for what's the rotational inertia. Okay, so well, alpha was this many radians per second squared. That was given. R is this many centimeters. I'm going to convert that to meters, just so everything's in meters. So roll the decimal back 2 places, that many meters. And then the force is, say, so many newtons. Okay. You guys see there's going to be one algebra step to get to the answer. Just divide the sides by alpha. Divide the alpha over. Okay. So this many meters times this many newtons. Okay, so there's the applied torque. Divide by how many radians per second squared, and that will give you I is equal to this many. Guys remember what the unit for that is? The unit. Here's a hint. For a single point, I for a point. You guys remember it's mr squared, and then more generally it's the sum of mr squared. And then there was like that table of values in the book for specific shapes sort of thing. Okay. So mr squared, that'd be kilogram meter squared, right? So this is kilogram meter squared. Okay. That's good. So that's how much rotational inertia it has. You know what, too? Dig through you guys' book real fast here. Okay. Because this is sort of related to something I want to remind you guys about, haven't seen in a couple weeks. Okay. You guys remember this table of rotational inertia values? Okay. So for a single point, it's just mr squared, but hey, look at that for a ring. Okay. Now, for a ring, it's also mr squared because every single point individually is mr squared, so the net effect is just also that. Okay. And I bet that shape would probably best approximate a bike wheel too, wouldn't it? So if you need the mass bit and radial size bit, something like that. But we could even use that to estimate what the mass of this bike wheel is. If we wanted to go that direction, do that too. Is that all? Yeah, it's all on 84. Okay. Number 88. A car's specifications state that its weight distribution is 53% on the front tires and 40% on the rear tires. Okay. So it's approximately 50-50 split, but not exactly. It's a little bit more on the front and back. The wheel base is so many meters. Where is the car's center of mass? You know what this problem reminds me a lot of is this demo that's hanging in front of me right now. You guys remember this? So I'm going to take this weight, just shift it right to the 50 centimeter mark. Right? And look at these two spring scales at the end of this meter stick. See how it's like half and half? Right? But if I take this weight and I shift it over closer to one side, remember one side picks up more weight, the other is less. Right? And we solved this back in the notes. I know this is like a couple weeks ago. Right? But here, maybe this weight is shifted slightly off center, then one side is a little bit more and one side's a little bit less. But hey, maybe kind of like this car. Notice that they never actually gave you the weight of the car. They just told you the wheelbase and some percentages. But we can figure this out there. So 88. Okay. So, you guys remember we solved this whole meter question with torque also, right? So it's probably going to be a torque question. Okay. So let's get a car going. It's got a rear wheel and a front wheel. Okay. And the wheel base, let's say from axle to axle. Okay. Maybe I'll just call it an even 3 meters. I'll call this a distance of 3.0 meters. Something like that. Okay. And the center of mass of this car should not be at the geometric center, because if it was, it would be a 50-50 split on the wheels, but it's not supposed to be exactly that. I'm going to exaggerate this a bit, but I want to shift the center mass over just a little bit. So here's your center of mass, right? So that the front wheels should take a little bit more weight than the back wheel. Okay. Let me do a free body diagram, FBD, free body diagram, so I can get some forces on here. Okay. So I'm thinking 3 forces I have to think about. Now, the whole car has a mass and a weight, but I'm going to treat it acting at the center mass, which is like straight down. Okay. And that's some value, well, we don't know. I'm going to call it mg. Okay. If that's really confusing, then you could always just make up a number, call it like 1,000 newtons or something like that, right? And then figure out from there. Okay. Because if it works in general, it should work for any specific case. Okay. Now, the front wheel is holding up a little bit more than half the weight, and the back wheel is holding up a little bit less than half the weight. Okay. So force right, hold on. The right force and the left force. I don't want to call it that. Okay. I'm going to call it 53% of mg and 47% of mg. Just like that. That makes sense. Okay. Right. Again, if that's like super confusing, you can just say the car's 100 newtons of weight and 53 newtons are on this wheel and 47 newtons are on that wheel, something like that. But I do want to show you guys that the mg is going to cancel out at some point too. Okay. All right. So I remember how we were solving this meter stick question a couple weeks back, which is something to do with torque, and I had to pick a pivot point. And I did tell you guys that you can pick any point and treat it as the pivot point, and the torque should still zero out. And the torque has to zero out. Here, there's 2 conditions for equilibrium. The sum of the forces is 0 newtons, and we took care of that already because these 2 add up to this one. Okay. But also the sum of the torque is 0 newton meters. Okay. But I have to pick a pivot point. So I'm going to pick, say, the rear tire. Okay. Oh, I forgot to label the question. The question is this. What is this value x? Okay. That's what we're trying to solve for. What is that distance x? Okay. So I'm going to treat this right here as the pivot point. Kind of arbitrary. Pick any point, this will still work out, but pick that one. Okay. And so if I do that, from that point of view, you guys see that the car's weight itself, say if it's pivoting on the rear tire, is trying to turn this whole car clockwise. So I'll call this torque clockwise. Okay. And the normal force on the front tire is holding the car back in check with some counterclockwise torque. Right? And if the second equilibrium condition is true, then these two torques have to be balancing each other out. You see it? So the car trying to turn this way because of its weight, and the car being held back because of its the normal force on the front tire, those two are going to balance out. Okay. If I do, I think I told you guys about right-hand rule, which, so R cross F into the page for this one, and then R cross F out of the page for this one. Right, if you like right-hand rule. Okay. So some of the torque has to be 0. So I know that the torque clockwise plus the torque counterclockwise has to be 0 Newton meters. Now the clockwise torque, that is the weight, well, R cross F. You guys remember also torque is R cross F. Write that up here, torque. Torque equals R cross F. Okay. So R cross F. So that's this radial distance of X times the force of the weight of the car, mg. Okay. Again, even though the weight of the car is technically distributed everywhere, I can treat it as its center mass. Everything's perfectly fine. Okay. Plus this other radial distance, which is the axle base, the wheelbase. Take that as just 3 meters. Multiplied by the upward force, which is 53% of the weight. 50. 53% of the weight. Okay. Now, one more thing about the setup is that these two forces, notice that they're in opposite directions. One is acting down, the other is acting up. Okay. So I'm going to represent that with how? Maybe a negative sign. Right? Doesn't one of these have to be the opposite sign of the other? So I need to throw in a negative sign somewhere. Okay. Kind of a technical thing because we're really close to finishing this off. I'm just going to add this term over and then divide and then get the answer, right? He said, you know what? Actually, I can just take care of the divide part right now because I got these two terms. What do they have in common that's just going to cancel out anyway? BMG, yeah. So remember how they never told us the mass or the weight of the car? Well, here's where it cancels out. Different cars, different masses, doesn't matter. Hey, you could even take this car to different planets. Take the whole thing to Mars, take it to the moon, and the answer is going to work out the same anyway. So that's all good. Right? So just got this times this. I'm just going to add that over, and then that'll be it. That's the whole thing. So try that out. So it's 3 times 0.53, adding it over, so it'll become positive again. X must be 1.59 meters from the rear wheel. From the rear wheel. Maybe that kind of makes sense because remember, if the center mass of the car was exactly its geometric center, then the wheels should be like 50-50 split for the weight of the car. But if the front wheel is carrying a little bit more than half the weight, which it is, then the center mass should be shifted a little bit that way, which I drew it that way. And hey, look at that. It's a little bit more than 1.5 meters because 1.5 meters would have been exactly halfway. Yeah, that checks out. Makes sense. All right, number 90, topsoil. I got 10 bags of topsoil, each weighing so many newtons, placed on a big old sheet of plywood. Yeah. Okay. They're stacked this many meters from one end sheet of wood, or just like it shows. 2 people lift the sheet of wood, each at one end. So you got one guy over here lifting, one guy over here lifting. Ignoring the weight of the wood, right? So the plywood itself is very small mass compared to the bags of topsoil. What force should each person exert? Right? Who's going to apply more force to lift? The person on the left, the person on the right, or do they exert the same force? What do you guys think? Let me see, show of hands. How many of you guys think that this guy on the left has to apply more force to lift? No, nobody says that. Who says the guy on the right? Yeah, that's gonna be the answer, right? So it's gonna be the guy on the right has to exert more force, right? So we got that down anyway. Okay, but what exactly? Can we solve for some numbers? Let's try this out. Okay, number 90. Alright, so big old plywood, couple of guys lifting, okay, and a big old stack of topsoils right here. Okay. Hey, you know what? This is actually looking pretty similar to the carb question I'm thinking, and also kind of similar to like this meter stick hanging from the ceiling here. Okay. I think it's gonna be the same sort of category question, maybe something to do with torque. That will do. Okay. They said 10 bags each weighing so many newtons. So when you have to take the newtons per bag and multiply by 10 bags, something like that. Okay. I'm just gonna go ahead and write in a full number here. Okay. You know what, I'll make it an even 1,000 newtons. Say this is just like 1,000 Newton downforce. Okay, nice round number. Now for you guys, it's gonna be more than that, but for your textbook. Okay. I'm thinking that this guy on the right, just like you guys said, is probably holding up most of the force. I'll call it F sub R, like the right force. And this guy on the left, well, he's applying an upward force too, but not as much. So force sub left. Now, how much force they each apply has something to do with where the topsoil is located. So let's say, to get some numbers right. Let's say this whole thing is like 2.0 meters long, and it's like 1.5 meters to that point. Yeah. Okay, so that's the setup right there. Right, so notice that there's two unknowns. Now this is well, it's not exactly like the card question, so it's a little bit different. But okay. But we're going to apply really similar thought process to solving this. Right? So I need to pick a pivot point. I'm going to pick this point on the left, just like I did for the last question. Okay. So here's my pivot point, just to solve the question. Really, to pick any point. But there are 2 points that are more opportune to pick as pivot points, and it's either one of the unknown forces. Why is that? Because if you have a set up the equation so it's like sort of rotating about one of the unknown force values at that point, okay, then that force does not actually apply any torque to the pivot point, right? Kind of like if you start pushing on the hinges of a door, well, that's not going to rotate the door, right? So yeah, you could pick either one of these, but just pick one. So now, from that point of view, it looks like the topsoil is trying to rotate this whole platform clockwise, okay? And this guy holding it up is, well, that's going to be a counterclockwise torque. Okay? And let's think about our equilibrium conditions. So you know that so for equilibrium, two conditions now. The sum of the forces in each direction has to be 0 newtons, in this case, like the y direction. Okay? And also the sum of the torque about any point has to be 0 Newton meters. And one thing that you can see right away is that these two forces have to add up to the full 1,000 newtons. Right? That's the top condition. Okay? But the new stuff is something to do with that torque right there. Okay? So we got torque clockwise and torque counterclockwise. Okay. Right. You guys are that so far? Okay. And you know what? The bell's going to ring here in about 30 seconds, so we have to. Oh, no, it isn't. No, it isn't. Sorry, we got a full 2 minutes. Okay, see if we can do this real fast. So torque is R cross F. Okay. Let's take this radius of 1.5 meters crossed with this force of 1,000 newtons plus this full 2 meters crossed with the force of F sub R, the right force, which is unknown, that has to zero out. Okay. So this is 1,500, subtract that over, divide by 2, just algebra, right? It's 1,500 negative divided by 2. Okay. I'm looking at right force on the right side of negative 750 newtons. Okay. Now it's negative because the weight I assigned is a positive number, so up would be the opposite. That's why it's negative. Okay. Is that okay? So sum of torque has to zero out. See a little bit of algebra shuffle. Get that? Okay. Now if you know that, and you also know that the total force has to zero out, then what's the force on the left side? Negative 250, exactly. So negative 250 plus 750 plus 1,000, exactly zeroes out. Okay. All right, that is much better PowerPoint. Oh, yeah. All right, we'll pick up from there tomorrow.